Hello everyone, I'm Yunze Xue. Today I want to introduce you an interesting work I did with my advisor, Uzman Roshan. Image classification and retrieval with random depthwise signed convolutional neural network. In the real-world classification problem, we can hardly use a linear method to deal with most datasets, because most of the data points are nonlinear separable. The left figure is an example. We can't use just one hyperboline to split these two classes, blue stars and transparent circles. A commonly used way to deal with this kind of problem is the kernel method, which projects data points from a lower dimensional space to a higher dimensional space. And we hope these data points can be linearly separable in the higher dimensional space. Except for the kernel method, there exists another method to do it: multi-hyperplanes. We can utilize several different planes to split data. It's a little like a decision tree's decision boundary. In single-layer random hyperplane network, we can join several different hyperplanes based on different parameter sets. Each hyperplane is decided by a set of parameters. Then we use the sign of the dot product of W and X to replace original features. Figure 2 is an example with 4 hyperplane. Let's look at the green line. We can treat it as a hyperplane, and this line is decided by a set of W, W0 and W1. So all data above the green line will be assigned 1 in the new representation, and 2 circles below the green line will be assigned 0. Each line here will give each data point a new representation value. 4 lines will give them 4 numbers. So in new representation space, each data point will be represented by a vector whose length is 4 and only contains 0 and 1. If there are k lines rather than 4 lines, the length of the vector will be k. Here, each parameter set is randomly generated. Then we can train a linear classifier like linear SVM or a single-layer neural network to do classification based on the new features. Because new representation is better for some basic machine learning algorithms. We can also think new representation is a projection, and the data points become more linearly separable in the new space. Image data is a little different because image data contains special information, so we can't easily flatten an image's pixel value to a vector and run a single-layer hyperplane network on it. Translation invariant means when we horizontally flip an image, this image's meaning will not be changed in most cases. Flipping operation would not affect humans to recognize images. Sensitive to color means we can recognize items by their color, like the ocean is blue, the grass is green, and the sun is orange. Currently, the convolutional neural network is one of the best tools to deal with computer vision problem. The deep neural network has achieved human-level performance on some large image recognition benchmarks. So I'm thinking that random-weight neural network will be a good alternative of single-layer hyperplane network on image dataset. When we are designing the random weights network to generate features for image data, we have to make sure images' spatial information can be considered in the network. And we also found that when we increase the number of random features, classifiers can achieve better performance. Figure 3 shows our network architecture. Our activation function here is a sign function. The output is either 1 or -1. After a convolutional layer, there are several downsampling blocks. In each downsampling blocks, there is a 2x2 average pooling and 2 convolutional layers. We decide the number of blocks based on the input image size. In general, we assign 2 or 3 to it. The final layer is a global average pooling, which means the network will give us a continuous number rather than 0 or 1, because we find the average value of the final feature map is better than flatten the final feature map. The global average pooling operation can bring a global receptive field. Networks with initialization is followed by the normal distribution, because in the beginning we will normalize the image to a normal distribution. If we want to generate a lot of features for an image, what should we do? In theory, we have to use K networks to generate K features. In each network, the number of filters is 1. Why we do that is because we hope the final features are independent of each other. Actually, we can use the depthwise convolutional operation to achieve better implementation efficiency. In the depthwise convolutional neural network, we don't need to create K networks for K features. We just need to build one network, but set the number of filters to K. This figure shows that we draw the pixel value distribution of different classes images in the original space and new feature space. In the original space, we can hardly distinguish two classes, but they look much more clear in the new space. Those images are from STL10 benchmark. I picked the first and second classes images to draw the plot. Here I want to show what the new features give us. In the left figure, we use the first image as a reference, and then we retrieve the top 15 most similar images to it on the new feature representation. We use Euclidean distance to evaluate their distance. We can see all these images have similar backgrounds, but there is only one bird here. Others are deers, dogs, and monkeys. We can say these images are similar because we can say these images are similar if we ignore the main object's classes. After we train a 3-layer network on the new feature, and we retrieve images based on the hidden layer's output, we find most images are birds now. This result is much better than training the same network on original space, which just flattens each image's pixel value. It shows the new representation makes multiple perception doing classification easier. This figure shows the results of network compared to some famous CN architecture like VGG16, ResNet, and DenseNet on some benchmarks. After we generate 100,000 features, we train a linear SVM on it. These benchmarks include Skyfa10, CIFAR100, SDL10, and Mini ImageNet. ImageNet contains 1,000 classes. To save memory, we only include 10 classes of it. We can see our network's results can achieve close accuracy to chained CN networks, especially when we exclusive data augmentation in the chaining, because data augmentation can help the CN in generalized performance, but it would not help our models. Our method's advantage is to find similar images. There is an image retrieval benchmark from Korea Princeton. In this benchmark, there are 8 classes. In each class, there is a reference image and some similar images, which is ranked by humans. This figure shows results about our network's performance in this image retrieval benchmark. It shows our best method is better than a chain CNN. In here, we include VGG16 and ResNet as a reference. But in some class, our model is not good. It's not good as chained CM because we find in those class the similarity is dominated by the items classes rather than the background or the main color of the images. Our method's biggest advantage is it's very simple. What you need to do is build a network and initialize the weights randomly, and you can use that network to generate a lot of features. And our model is support data parallelism and model parallelism, which means we can split the model each network into different machines, and we can generate features simultaneously on each machine. The drawbacks is when we increase the number of features, the number of random features we generate, the classifier can achieve better performance, but it is also very easy to overfit in a data set. And the biggest problem is if we want to use those features to do classification, those images' main color is very easy to dominate the classification results. But that is also an advantage if we want to retrieve similar images, except the main body, the main objects classes. Depthwise convolutional is the most important component in our networks, and you can find the detailed description in the exception paper, Deep Learning with Depthwise Separable Convolutions. Thank you.